So here's a quick recap. If you have this vector valued function and suppose that it's conservative, so you found the lowercase f and the gradient of the lowercase f is equal to the capital F. Then there's an easier way to do this integral. You just take that lowercase f, evaluate it. So f of b minus f of a, and then that's a faster way to do this integral. Now keep in mind that it's conservative if, yes, you could go ahead and find the f, but there's also this little shortcut. You take this, which is the y component, take the derivative with respect to x, which is really like finding the second derivative of lowercase f. And then take this one, which is the x component, take the derivative with respect to y, which again is finding a second derivative of lowercase f. If those are equal, it's conservative. Then, what if it's not conservative? So what if you take those derivatives and they're not equal to each other? So that means that you can't use this little shortcut. Or another way to look at it is that if you subtract them, it's not equal to 0. So then here's what Green came up with. Suppose that you're talking about this curve C and it's a closed curve. And just like in Math 3A, if you integrate in the correct order, you get a positive. If you integrate in the wrong order, you get a negative. So this is called the positive orientation. So it's going around this way. And then that's curve C. And then you're supposed to calculate the amount of work as you go around this little lake right here, around the outside. So in other words, you're supposed to integrate around the curve C, p times dx plus q times dy. And sometimes to distinguish and say that it's a line integral, they'll put a little circle right there when it's around a closed curve. Okay, but anyway, you're supposed to do that, and you're looking at it, and it's a lot of work, and you need the parameterization of curve C, etc. And then you're going to have to substitute those in there, and you're like, is there a faster way? And Green goes, yeah, there sure is. Turn this into a double integral, and then take this difference, which is not equal to 0, and then you integrate over the area. So instead of going around the outside, you then integrate over the area, and that red part is going to be called the region D. So then integrate over that region D. And then this is an easier, faster way to do that integral. So for example number 1. Suppose it's a line integral, x squared dx plus xy dy. And you're looking at that saying, hey, that's not too bad. I could integrate with respect to x, that's x cubed over 3. I could integrate with respect to y, that's going to be x times y squared over 2. That's Math 3A. And then the curve C, so this is over the curve C, and then the curve C goes like this. So it's actually going to be a triangle. So you go this direction, then you go this direction, and then you go back to the origin. So then integrate over the curve C. Well, that means that we would need a parametric function that gives you this line segment, a second one that gives you this line segment, and a third one that gives you this line segment. So you would need to do this actually 3 times. Or you could use Green's theorem and integrate over the area. So for one thing, this line right here, this has a slope of -1 because it's intersecting at 2 and also at 2. So this line is -x plus 2 because the B part would be where it intersects the y-axis. And this is P and this is Q. So then it goes, change this into a double integral, and then it's going to be Qx. So take this one and take the derivative with respect to x, which means that it's just y, minus take this one and take the derivative with respect to y. And the derivative of this with respect to y is 0. And then integrate over the area. So I think I should have replaced this and just say I'm going to do dy and then dx. So as it goes over the area, the y, I would have a little rectangle right here that represents that little portion of area. And then y goes from 0 at the bottom to negative x plus 2 at the top. And then x is going to go from 0 to 2. And that's it. We don't have to do 3 integrals. This is it. Just integrate, basically just integrate y. So that would be y squared over 2, evaluated from 0 to negative x plus 2. And then we'll still need to integrate with respect to x when we're done with this. So this would be the quantity negative x plus 2 gets squared over 2, or I could factor out the half, and then it's going to be negative x plus 2 quantity is squared. And then of course when you put a 0, that's 0. And then we could just integrate this. This is going to be raised to the third over 3. And then because of the chain rule, the derivative of the inside is a negative 1, so I'd need to multiply by a negative 1. And then that I would just put together with this 1/2. And then it gets evaluated from 0 to 2. So when you substitute the 2, this is actually going to be 0. So it's going to be 0 minus. And then when you substitute 0 for x, this is just going to be a 2 gets cubed, so that's 8. 2 cubed is 8, and then it's over 6, and it's minus the negative, and it's 8 over 6. So in the end, it's positive 8 over 6, or 4/3. Then for the next example. For example number 2. Integrate, and it's a line integral, y to the 4th dx plus 2x y cubed dy. And again, you look at that and say, oh, that's not too bad of an integral. I could do that pretty easily. But then the curve C is x squared over 4 plus y squared over 1 equals 1, which is an ellipse. And it's going to intercept the x-axis at negative 2 and positive 2, the y-axis negative 1 and positive 1. So that is the curve C, that ellipse right there. So if we're going to use Green's theorem, this is the P, this is the Q. So you start with this one and take the derivative with respect to x. So that means this becomes a 1. So we get 2y cubed. So it's going to get changed into a double integral. And then it's going to be 2y cubed minus. Now take this one and take the derivative with respect to x, with respect to y. So that's going to be 4y cubed, which is nice because that means that this is just going to turn out to be negative 2y cubed that we integrate. And then we would need to put like dx and dy. Well, if you do this directly, then x is going to equal, so let's see, we would need to subtract the y squared. So it'd have 1 minus y squared. Then to solve for x, we'd also need to multiply by 4. And then to solve for x, we would also need to put plus or minus the square root. And so if we're doing dx first, that means that this is going to be that negative square root, and this is going to be the positive square root. So maybe there's even an easier way to do that, because that is not looking so easy. So is there an easier way? So for an ellipse, we could basically change it to polar form. And in polar form, an ellipse is going to look like x equals 2 cosine theta, y is equal to sine of theta. So that way, if I substitute this in for x, that would say 4, once you square it, it's going to say 4 cosine squared, and then the 4's will cancel. When you substitute this, it's going to say sine squared. So what would be left is cosine squared plus sine squared, sure enough, does equal 1. Okay, so that's an ellipse. Now, the only problem is if we're going to use Green's theorem, which is what I started doing right here, then we need to know the area. So this is just the ellipse. So this only gives us the outer edge. In other words, going around the outside of the ellipse. What if we need the area? So we just need to adjust this a little bit. If you need the inside area, then you use x equals, and just multiply this by r. 2 times r cosine theta, and y equals r times sine of theta, where r ranges between 0 and 1. So basically, when you have this, that means that the x value has to be all the way out here on the ellipse. So basically, it has to go all the way out to there, and it has to be stuck on the outside of the ellipse. But if r was equal to a half, that would cut this in half, so then it would be right here inside the ellipse. If you have r equal to, say, a 0.9, then it's going to be here. If it was a 0.1, it would be here. So, etc. As r ranges, it's going to have all of those values on the inside. So this will create the inside area. Now, the only thing is, this is a change of variables. Which means that we need the Jacobian. So for the Jacobian, set up a little 2 by 2 determinant. And then for this x function, we need to take the derivative with respect to r. So that's going to be 2 cosine theta. And then we need to take the derivative with respect to theta. So that's going to be, this part will just stay there. And derivative cosine is negative sine of theta. And now for the y function, take the derivative with respect to r. So that's just sine of theta. And then take the derivative with respect to theta. So that's going to be r cosine theta. And then find the determinant. So multiplying this way, it's going to be 2 times r, and then cosine times cosine. And then minus, when you multiply these two, that's going to be negative 2r times sine squared. And then these two negatives will become a positive. Then I could factor out 2r. And what would be left is cosine squared plus sine squared. which equals 1. So that means that the Jacobian equals 2 times r. Okay, so back to the setup. So we had done this much. So this reduces to be negative 2y squared. So we're going to have a double integral, and then it's negative 2, and y, excuse me, I just said squared, cubed. The y needs to be cubed. And the y is equal to that one right there. So sine of theta needs to be cubed. And then we need to put the Jacobian right here, which is going to be 2 times r, which is good because when you change to polar, you have to put an r, and that's where the r comes from, is the Jacobian. And then dr, d theta. And as I mentioned just right here, r is going to go from 0 to 1, and theta, so you need it to go, this little arm right here needs to go all the way around the clock, so that's going to be from 0 to 2 pi. Okay, so that's the setup for this one. Now we need to integrate. Integrating the r, that's not going to be a problem. You know what? I think I left off a little r right here. I was pointing to the wrong one because I had papers covering up. I'm missing a little r right here. That's why I left that space. My brain was saying, what about the r? Okay, so anyway, this would be an r cubed together with this, so that's going to be r to the 4th. That's easy to integrate, not a problem. Integrating sine cubed, so that, if you were going to do it, but I'm going to even go for a shortcut on the shortcut. So if you were integrating sine cubed, then you would need to factor it as sine squared times sine, and then replace this sine squared with 1 minus cosine squared. And then do u substitution, and the u will equal the cosine part. And so this is basically going to become 1 minus u squared. And when you take the derivative of cosine, it's negative sine, so this is going to become negative du. So that's what we would be integrating. But the thing is, since it's from 0 to 2 pi, take a look at sine cubed. So y equals sine cubed function from 0 to 2 pi. Oh, my calculator's in degrees. So take a look at that function. Now, if you integrate that from 0 to 2 pi, this is going to be positive something, and because the graph is symmetric, this is going to be negative the same amount. They're going to cancel each other out, so it equals 0. So after all of that, turns out that the answer is 0. Now, there's one other thing that we can do with Green's theorem. So when we first started doing double integrals, if you integrate just dA, and then you put the limits, so whatever the limits are for the region, and you do this double integral, but you put nothing here other than dA, this is going to give you the area of the region. Now you could look at it as, right there is a 1. So what if you are doing Green's theorem, and right there you were supposed to put the derivative of q with respect to x minus the derivative of p with respect to y. So in other words, what if this happens? Well, how could that happen? That could happen when Q is equal to X and P is equal to 0. So, in other words, if you have a line integral, P times dx plus Q times dy, so then according to Green's theorem, that would equal the double integral of Qx minus Py, and then integrate over the area. But if this was x, its derivative with respect to x would be 1, that one would be 0, and then look at what happens over here. So in other words, this one would be 1 minus 0 dA once I simplified the right side. When I simplify the left side, P is 0, so this is gone, and Q is equal just an x. So the line integral of x times dy is equal to the area of the region. So that is pretty weird. So this is saying go outside of a region and integrate as you go along the outside of it. And as you go along the outside of it, that will tell you the area on the inside of it. So it's basically saying, here's a region, you walk along the outside of this lake. And as you walk along the outside, you integrate x times dy. And that will tell you the surface area of the lake. All right, now let's actually try it. So for example, number 3. Find the area of an ellipse. So this is the same ellipse that we had before, so you could still use that x is equal to 2 cosine of t, y is equal to sine of t. And then if you graph that in parametric form, it gives you an ellipse. So according to this shortcut, the area is equal to the line integral of x times dy. So x just means substitute 2 times cosine of t. dy means take the derivative of this, and the derivative will be cosine of t. And then in order to create the whole elliptical shape, then t is going to need to go from 0 to 2 pi. Well, this right here is cosine squared, and in order to integrate cosine squared, we need to use the formula 1 plus cosine of 2t divided by 2. And then we can have these 2's cancel. So the antiderivative of 1 will just be t. For cosine, it's going to be plus sine of 2t divided by 2, and then evaluate that from 0 to 2 pi. So this is going to be 2 pi, sine of 4 pi is 0, then substitute 0, so that's going to be 0, and that's going to be 0. So the only thing that remains is when I put the 2 pi in for t, so the area is 2 pi.